All right, today we're going to dive into a topic that I know sounds a little intimidating: chemical thermodynamics. But hang in there with me, because this is not about memorizing a bunch of equations. Nope. Think of it as a secret decoder ring for figuring out what can and can't happen in the world around us. And really, it all kicks off with one simple question.
You know, when you get right down to it, almost everything in chemistry, from a campfire to a rocket launch, boils down to this one question: will it happen? Are these two things I just put next to each other actually going to do anything?
And this gets really interesting when you think about the possibilities. I mean, some reactions are just bam, an explosion, over in a flash. Others, like a car turning to rust, take forever. And some, well, they just won't happen at all. So how on earth do scientists predict what's what?
Well, the answer isn't just a lucky guess. It comes from a whole field of science that was designed to do exactly that, to make that prediction. And it's all about energy. That field is called chemical thermodynamics. Now, I know the definition sounds pretty formal, but the idea behind it is actually super simple. It's really just the science of keeping tabs on energy as it moves around and changes form during any kind of process, whether it's ice melting in your drink or fuel burning in an engine.
And you see this idea of energy conversion literally everywhere. Think about it. A battery isn't magic, right? It's just converting the chemical energy stored inside it into electrical energy that powers your phone. Or look at a waterfall. That's just turning the potential energy of the water up high into the kinetic energy of motion as it comes crashing down. It's all just energy-changing jobs. Okay, and this is where things get really, really cool. Because if you can track where the energy is going, you basically get a superpower. You get the power of prediction. Here's the key. By following the energy, thermodynamics lets you kind of peek into the future of a chemical reaction. It can tell you if that reaction is feasible, if it's something that can happen all by itself, without any outside help.
And it actually gives us two major clues. First, it answers that big yes or no question. Is this reaction even possible in the first place? And second, if the answer is yes, it can predict how far that reaction is going to go before it kind of runs out of steam and finds its balance point, its equilibrium.
But, and you knew there was a but coming, right? This is a really important one. For all of its amazing predictive power, thermodynamics has one enormous blind spot. There's one critical piece of the puzzle it completely ignores. Let's talk about diamonds. According to the laws of thermodynamics, the carbon atoms in a perfect diamond would actually be more stable if they rearrange themselves into graphite, the stuff in a pencil. The reaction is totally feasible. So why isn't your jewelry turning into dust? Well, here's what thermodynamics hides. That process is so mind-bogglingly slow, we're talking billions of years. It's pretty much unobservable. And that reveals its fundamental weakness. Thermodynamics can tell you if a thing can happen, but it, and I quote, provides no information about the rate at which the reaction occurs. It is completely silent about speed. It has zero concept of time. It doesn't know if a reaction takes a nanosecond or a billion years. So how do we make sense of this? How can it be so powerful, but also have this massive limitation? Well, the absolute best way to think about it is to compare the destination to the journey. Think of chemical thermodynamics like the GPS in your car. You punch in a destination, and it tells you, yep, that place exists, you can get there. But your GPS has no idea if you're about to hit a 5-hour traffic jam. For that, you need a different tool. You need a live traffic report. And in chemistry, that traffic report is a whole other field called chemical kinetics. It's the part that studies the rate of reactions. It's the part that tells you how long the journey is actually going to take. So let's just quickly recap the big takeaways here. First, thermodynamics is amazing for predicting if a reaction can even happen. Second, and this is crucial, it tells you absolutely nothing about how fast it will happen. And finally, to really, truly get the full picture of what's going on, you absolutely need both. You need the GPS to know the destination is real, and you need the traffic report to know how long you'll be on the road. And that kind of leaves us with a bigger thought, doesn't it? Thermodynamics is all about the endpoint, where you're going to end up. Kinetics is all about the path you take to get there. And it makes you wonder, both in a lab and, just in life, what's really more important, the destination or the journey itself?